Welcome to UGC E-Pathshala lecture series on computer science. The course is on visualization techniques, and today's module we are going to look at animated visualization. So the learning objectives for this module are: it introduces the need for animated visualization. It is possible for us to know the different types of animated visualizations. We can also learn about the evaluation techniques that gets applied over the animated visualization, and we will also have a look at various examples of animated visualization. So now let us look at the need for animated visualization. Animated visualization is still a new area. A two-dimensional image is actually good so that we can understand that a moving image should be better than a two-dimensional image. Movement is familiar, and we are accustomed to both moving through the real world and seeing things in it move in a smooth manner. In a visualization, animation might help a viewer to work through the logic behind an idea by showing the intermediate steps and transitions, or show how the data gets collected over time changes. A moving image might offer a fresh perspective or invite users to look deeper into the data presented. An animation might also smooth the change between two different views, even if there is no temporal component attached to the data. First, let us have a look at what trend visualization is. Animation can be applied over trend visualization technique. Animation has been used to show the trends in multidimensional dataset. This technique has recently gained new prominence, notably with the tool named Gapminder Trend Analyzer. In Trend Analyzer, the animation together with the interesting data and an engaging presenter helps the audience understand the results of an analysis of a data. The two alternative trend visualization that use static depictions of trends are the one which shows traces of all trends which are overlaid simultaneously in one display, and the second that uses a small multiple display to show the traces side by side. It evaluates the three visualization for both analysis as well as presentation, and the results indicate that the trend animation can be challenging to use even for presentation. While it is the fastest technique for presentation, participants find it enjoyable and exciting, and it does lead to many participation errors. This is an example of animation and trend visualization. This actually shows small multiple views in which each country in its own tiny coordinate system. The dots grow larger to indicate the progression with respect to time. This is also another example of trend visualization. These are frames of animation from the Trend Analyzer tool, which is used for the study. In the tool, the image smoothly animates between images at 1 year intervals. All images share the same axis. Note the convergence of most countries moving towards the bottom right hand side corner. Over high life expectancy, low infant mortality. The fourth frame highlights one country which has a counter trend. Here we can see the difference between this country and the various other countries which move in the same manner. Next one is animation visualization with respect to time series data. Depicting changes over time in the position or attributes of geographical phenomena form a constant viewpoint. That is, change in chronological space is the most obvious application of animation in both the social as well as the physical sciences. Time series sequences are ordinarily constructed from scenes sampled at intervals along the range of the series, viewed in a chronological order at a constant rate. Each scene is viewed for about 3 seconds, and one map gradually dissolves into the next. The most elaborate scientific animation known to us, which is called as a study of numerically modeled severe storm, explores the physical structure of a simulated cyclogenesis event as it evolves during a 2-hour period. The invisible structure of the internal winds is artfully represented through the translucent shell of the storm with traces, buoyant balls and streamers. The video was produced during a 11-month period, requiring the equivalent of one person's full-time effort for more than an year. The animated portions of this 7.5-minute tape took about 200 hours to render on a graphics-accelerated Silicon Graphics Iris workstation. The time series can also be created from scenes representing such time aggregates as an hour, a week or a month. Weber's animated isotherm map, the result of such an aggregation procedure, is termed as collapsed real time. So now we'll see, we'll have a look at this Weber's animation. This is a Weber's animation. Here we can see the animated display of the entire isotherm map. So this is one particular area that we are looking at, and each and every color represents a different, say, the temperature with respect to whether it is frozen or rainy or what is the temperature at each and every location can be identified just by looking at this animated visualization. So next to time series data, alternatively, the time series data can also be treated as cyclic with aggregate values depicted for positions in the circuit. Morling is a person who used this procedure to create what he called as a composite week, during which accidents were displayed for 15-minute aggregates. An aggregate time series in which the locations of 27 catastrophic earthquakes from 1900 to 1990 have been collapsed into 5 scenes, and that is being shown here in the form of a time series animation. So this is visualization of the chronological change of the time series data, 27 scenes, each showing about one catastrophic earthquake, and are shown as 5 composite scenes here. We can also look at the attribute change, and that can be represented in the form of animation visualization. So here in this case, the focus is given to the change in position of the object in the attribute space. The term re-expression is used to denote alternative graphic representation whose structure has been changed through some transformation of the original data. Simple examples from graphing include transforming linear measurement scales to logarithmic and applying smoothing filters to unmask a pattern in noisy point scatters. In the context of cartographic visualization, the analyst can choose the strategic subsets of time series sequences, which is called as brushing. He can alter the order, which is termed as reordering, and he can also make rhythm of sequences, which is called as pacing. So brushing is a very high interaction technique which is used for analyzing multivariate data. Brushing allows the analyst to see the interdependence of subsets of data for a variety of variables simultaneously. This technique was extended by Montmoyer in the year 1989 to a geographic context. He suggested having linked scatter plot and a map on the screen together so that when points on one part of the scatter plot were selected, the geographic location would be highlighted. Conversely, when regions on the map are highlighted, points in the plots corresponding to those regions would be identified. In the context of animation, brushing allows the analyst to select and view changes in a subset of data in geographic, chronological, or attribute space. Reordering next is shuffling the scenes of an animation in a purposeful way. Time can be conceived as a vector that can be divided into ordered intervals. If time is employed as a measurement scale, as it is in the dynamic mapping, any ordered or ranked data distribution can be matched and exchanged with it. They exploited the dynamic variable order in the sequential presentation of closed choropleth maps. They created a series of scenes from a single choropleth map by isolating each data category, and then they presented the scenes in the ascending order. Next comes the animated 3D visualization. The task of managing and accessing large information spaces is a problem in large-scale cognition. The emerging technologies for 3D visualization and interactive animation offer potential solutions to this problem. One of these information visualization technique is called as a cone tree. It is used for visualizing hierarchical information structure. The hierarchy is presented in 3D to maximize effective use of available screen space and enable visualization of the whole structure. Interactive animation is used to shift some of the user's cognitive load to the human perceptual system. The tree cone is an hierarchical structure. Cone trees are hierarchies which are laid out uniformly in 3 directions. The top of the hierarchy is placed near the ceiling of the room, and it is at the apex of the cone with its children placed evenly spaced along with its base. The next layer of nodes is drawn below the first with the children in cones. The aspect ratio of the tree is fixed to fit the room. Each layer has cones of the same height. Cone base diameters for each level are reduced in a progression which ensures that the bottom layer fits in the width of the room. The body of each cone is shaded transparently so that the cone is easily perceived. It does not block the cones behind it. When a node is selected with a mouse, the cone tree rotates so that the selected node and each node in the path from the selected node up to the top are brought to the front and are being highlighted. So this is a layout of a simple cone tree. This is before the selection and this is after the selection of a specific node, so that only the nodes that are attached to this specific node are being highlighted and shown here. The rotations of each structure in the case of hierarchical cone are done in a parallel fashion following the shortest rotational path and are animated so that the user sees a transformation at a rate the perceptual system can track. The tree can also be rotated continuously to help the user understand the substructure or the relationships. The display of the node text does not fit the aspect ratio of the cards very well, and hence the text is shown only for the selected path and showed as an alternative layout called the cam tree, which is horizontally oriented and has text displayed for each node. Interactive animation is used to shift some of the user's cognitive load to the human perceptual system. So this is an example of the cam tree. This is the layout of a simple cam tree before the selection. In the case of a cam tree, we can see that the text is laid beneath by the side of the nodes itself. And this is a cam tree example after the selection of a specific node. Next comes the story visualization. Story is defined as an ordered sequence of steps with a clearly defined path through it. Each step can contain text, images, visualizations, video, or any combination thereof. Focus is given on stories that primarily consist of visualization steps, which can include text and images but are mainly based on data. Order is a key feature of the story. In traditional stories, order roughly corresponds with time, which is crucial to understand the causality, that is, the events that happen earlier and influence later events, but not the other way around. Stories are often not told in a linear fashion, but rather use flashcards and other literary devices. However, within each segment, the order is consistent, and the order of different segments also needs to be made clear in order for the story to be comprehensible. They collect the information through research, interviews, etc., which gives them the key facts. They then tie those together into a story that may look very different and not directly use any of the source material like the data that has been collected through recorded interviews. In this model, the data analyst uses visualization for both the exploration, analysis, and for the presentation. However, the way it is being used can be very different. The choice of the technique will differ as does how much and which data is being shown to the end user. Visualization researchers often tacitly assume that the tools used for analysis are usable for presentation just as well for their original purpose. There are various storytelling scenarios. Each of these scenarios has different requirements for the techniques used, the way the presentation is structured, and the amount of interaction that is being anticipated. So based on which the storytelling scenarios are differentiated into three types: self-running presentation, live presentation by a speaker, and individual presentation. Self-running presentation is to a large audience, and this is a typical scenario for news media presentation. Here, a presentation is created once and then viewed by many people independently and without the ability to interact with the author or ask questions. Some of these stories are entirely self-running, for example in the case of a movie, and some require the user to click through, and some provide more or less limited means of interaction beyond simple timeline control. The goal of these stories is similar to that of a written feature story, getting a point across and explaining it in sufficient detail for the viewer to understand and to trust that the story is based on the real facts and data. In a self-running presentation, the key concern is often to draw the reader into it. For this purpose, they often present a static view that provides a teaser and a first bit of information that does not require any kind of interaction. This is similar to the form of a catchy title that are meant to pique the reader's curiosity and make them read the whole set of article. There are also often additional hints or affordances to direct the user to certain interactions to get the story started or to advance to the next step. In addition to informing about an issue, a story often tries to raise awareness and create interest in a topic a reader may not otherwise have been aware of. To provide a deeper connection with the story, it can allow the viewer to dig deeper into the data or at least find out how it relates to her by providing a map that she can focus on her immediate area. The next kind of storytelling scenario is a live presentation by a speaker. The live presentation by a speaker is done in front of an audience. This model, which is being exemplified by Hans Rosling, has a gapminder presentation, is similar to the way many business presentations are given today. The main difference is in it how the presenter can respond to questions, which partially obviates the need for an open exploration part at the end, but also poses other challenges. A presentation based on a live visualization allows the presenter to pause the story and interact in response to the questions. It is even conceivable that the presentation adapts to changes made at one point that carry forward through different presentation steps. In addition to the usual kinds of interactions used in visualization, there is an additional layer of annotation highlighting that can be useful in presenting. The next type of scenario is the individual presentation of results. The individual can also be some small group. While this scenario might not seem different from the previous one, it potentially involves more interaction between the presenter as well as the audience. This requires a presentation tool to be more flexible than a simple slideshow so that it is possible to answer questions that come up during the presentation. For example, in a discussion of quarterly results, questions about specific sales or marketing measures might come up that were not part of the story but are of interest to people in the audience. In addition to being able to ask and answer questions, it also appears useful to be able to record these kinds of questions asked so that they can be reviewed later. This way, the presentation becomes a vehicle not only for dissemination of information but also for collecting and condensing additional knowledge. The example of a storytelling visualization, the New York Times Copenhagen Emissions Treaties and Impacts. The slideshow controls allow the user to move back and forth between the steps, and the content is structured like a dialogue. In the story on the Copenhagen Climate Conference, the New York Times used slideshow controls to provide a way of stepping through. The story walks the reader through those differences and also shows the results of implementing the protocol in countries that has already agreed to it. While the slideshow metaphor is very simple, it allows almost any story to be told. This particular story has a he said, she said kind of structure, which is surprisingly engaging. So this is an example of the storytelling visualization. We can see the time series data with respect to the slideshow context. The next kind of animated visualizations are the animated networks. Graphs are a common way to visualize the relational data. In many systems, the drawing of a graph can change according to program or user interaction. If the changes are big, it is usually very hard for the user to maintain a mental map of the graph. Showing the transition from the initial drawing to the new drawing as an animation can significantly increase the user's ability to preserve the mental map of the graph. An animation, as said, is a sequence of images where consecutive images differ in a subtle but highly structured way. If the images are shown to human in consecutive order and at adequate speed, the objects in the images will be perceived as though it is moving, and this effect is also called as apparent motion. In graph animation, we move the nodes and edges of the graph to transform it from one drawing to the other. For any two drawings of a graph, there is an infinite number of ways to transform the initial drawing into the final drawing. So these are good examples of animated networks. We can see the entire network can be represented in different ways. The quality of animation has a huge impact on how well the user is able to understand the changes. The human brain is specialized to recognize and interpret certain kinds of structured movements, especially motions that have a physical, organizational, or biological interpretation. This is partly ecological and partly learned. The brain is also evolved to aid survival in the world and so tends to perceive or assume biological motions. The brain, while developing, also learns to recognize familiar patterns, structure, and motion that it encounters in the physical world. The next kind of visualization are the algorithm visualization. In the algorithm visualization, we have various examples of various algorithms that can be visualized in an animated manner. The basic algorithms on recursion, indexing, sorting, heap-like data structures and various other data structures like linked lists, queues, trees, graph algorithms, dynamic programming algorithms and geometric algorithms can be visualized in an animated manner. So, let me run a heap sort animation here. So, this is an animation of a heap sort. So, we can see how the entire heap sort takes place. We have various numbers and these numbers are arranged in the form of a heap sort and it is being animated as a heap sort animation. So, here we can actually see the various steps that happens to sort the entire data set as such. So, here in the UI we have two buttons for randomized array for creating the randomized array and for creating the heap sort. So, if we click the randomized array, the array gets randomized, and if we click the heap sort, automatically the animation starts running, and right from the first step to the result step it starts running in a automatic manner. There is not much of interaction in this case. So, as we have seen in the case of heap sort animation, there are other geometric algorithms or dynamic programming algorithms which can be visualized in this manner. Next one is evaluation of these kind of animated algorithms. We can ask the end users and we can evaluate by giving a questionnaire to the end user. So, here is an example questionnaire that has been given to the end user to evaluate the animated visualization that they have seen. So, some of the questions like the visualization was helpful to me in answering the questions. They try to rate it by giving certain values. So, this is some kind of evaluation that can be done over the animated visualization. There are certain laws like the laws of Gestalt that are supposed to be followed in creating these kind of animated visualizations. So, the certain laws are like the law of simplicity, which states that every stimulus pattern is seen in such a way that the resulting structure is as simple as possible. The law of familiarity, where things are more likely to form groups if the groups appear familiar or meaningful. The law of good continuation, which states that points that when connected result in straight or smoothly curving lines are seen as belonging together, and the lines tend to be seen in such a way to follow the smoothest path. Some other laws like the law of connectedness, where things that are physically connected are perceived as one full unit. The law of proximity, which states that the things that are near to each other appear to be grouped together. Next, the law of common fate, which states that things that are moving in the same direction appear to be grouped together. So, these laws are also called as the laws of Gestalt theory, which are actually used by the designers in turn for creating these kind of animated visualization patterns. So, there are certain downsides for these kind of animated visualization patterns. Let us look at some of the downsides of these kind of animated visualization. The animation has been less successful for data visualization than for scientific visualization. Two meta studies has been done to look at different types of animation, that is a process animation and algorithm visualizations, and they found that both classes of spotted track records when it comes to helping students more about complex processes. The animation did not seem to be helpful for process visualization, that is visualization that show how to use a tool or how a technique works. In no study was animation found to outperform rich static diagrams. But these kind of animated visualization did beat our textual representations, though, and simple representation that simply showed the start and end state without any kind of transitions. Algorithm animation is in many ways similar to process visualization. An algorithm can be illustrated by showing the steps that it takes place. Some sorting algorithms, for example, are very amenable to animation. An array of values can be drawn as a sequence of bars so that the sort operation moves the bars around, as we have seen in the previous example in the case of heap sort. Various other downsides of animated visualizations are: to understand the effectiveness of algorithm visualization in the classroom, half of the control studies they examined and they found that the animation did not help the students understand the algorithm as such. Interestingly, the strongest factor predicting success was the theory behind the animation. The visualization was most helpful when accompanied by the constructivist theory, what we have seen already in our previous modules, that is when students manipulated the code or algorithms and watched a visualization that illustrated their own work, or when students were asked questions and tried to use the visualizations to answer them. In contrast, animations were ineffective at transferring knowledge. Passively watching an animation was not more effective than other forms of teaching. There is a taxonomy of animation, that is, we can change the view of animation by panning over or zooming in onto a fixed image such as a map or a large data space. We can change the charting surfaces, that is on a plot, or we can change the axis on a map. We can change, for example, projection to a globe and things like that. Filter the data, that is, remove the data points from the current view following a particular selection criteria. We can reorder the data, that is, change the order of the points. We can change the representation, that is, we can change from a bar chart to a pie chart, change the layout of the graph and change the colors of the nodes by just interacting with this kind of animated visualization. We can change the data set in the case of animated visualization and see what happens, that is, we can move the data forward through a time step. We can modify the data, we can change the values that are being portrayed and see what happens. So this is also one simple example of animated visualization. We can see this is actually an animated GIF image, but here it is not working. It looks as though it is a static image. In this animation, usually the color and the numbers will be running through 1, 2, 3 steps, and accordingly when it comes to the first step will be portrayed here diagrammatically in an animated mode. Similarly for the second step and for the third step. So when this color moves to the first, when number 1 is highlighted, the first step will be depicted in the form of an animation here. These are certain examples of animated visualizations. So coming to the conclusion by summary, we can see that there is a total need for these kind of animated visualization, which helps students study the concepts in a more elaborate and understandable manner. And there are different types of animated visualization which can be applied over different types of data set. We can have graph data set, we can have cone trees, we can have hierarchical data set. Animated visualization can also be applied on stories and things like that. It can also be used for animating the sorting or some algorithms that are available. We have also looked at various examples of animated visualization, and we have also looked at how is it possible for us to evaluate these kind of animated visualization. The evaluations of these kind of animated visualization can happen only subjectively by providing some kind of questionnaires to the end users and by asking those end users to rate the visualizations that are provided to the end users. Thank you.